And he will talk about transmutation of lunar thorium for baseload power and nuclear rockets. So we're staying in nuclear power for a while. It's Peter Schubert, who is the emeritus professor.
I'm sorry, I'm not too skilled at. I'm trying to close this. I'm trying to stop sharing here.
Where you started sharing, you should be able to click to stop sharing as well.
Okay.
Yeah, I can kill you.
Okay, I think I see part of the problem. Yeah. Okay, there we go. Okay.
There. I found it.
Oh, what happened? There we go.
So, Peter, the floor is yours. Green Fortress Energy.
Thank you. Can you confirm that my audio is okay, Nicholas?
It is good.
Very good. Hello, everybody, and thank you very much for being here at near the end of the conference. I'd like to talk to you about using a lunar base for producing baseload power from in situ materials. This is a culmination of 6 years of research into this topic with a number of different publications. There's a paper that just came out in Advances in Space Research. So I've got this available. If somebody would like this, send me your postal address and be glad to send you a reprint of that. That has more than is what is presented here. This topic goes much deeper into the lunar aspect of that. The topic of the paper is mining of platinum, and I'll touch on that briefly in this presentation. This is the abstract for the talk. I'm not going to read this, but there's a couple of bolded topics that I want you to kind of very quickly skim through. Those are the things that I'll talk about in more detail here. So one of the motivators for this is that attending a lunar conference in 2019, I heard people bemoan the lack of power, electric power, to be able to do the science, exploration, manufacturing that they are interested in doing. And, you know, with solar power being mostly only half the time, maybe some peaks of eternal sunlight that are much higher than that, but with other challenges, everyone was hoping for a nuclear reactor on the moon. The 10 kilowatt versions of kilopower that NASA was working on are okay for small science experiments, but we're all interested in larger operations. So we need something in the megawatt class. Launching a nuclear reactor from the surface of the Earth, there's issues with outer space treaty where you could say we need to avoid harmful contamination by going into space, and even the best rockets are rated at 1% failure rates. Average over all rockets is about 5%. So the chance of blowing up a nuclear reactor in the Earth's atmosphere is something that, from a commercial standpoint, is very unlikely to be approved or be very unpopular. It'd be a mess. So the idea is, how can we ship machines to the moon to be able to use the resources there to produce nuclear power? So our motivation, of course, is to survive the lunar nights. I'm particularly interested in extracting metals, silicon, and oxygen. I've got 3 patents on how to extract those. They all take power. I start off with those being based on solar power. The yields are not very impressive, but with a large source of electric power, they're awesome. Water extraction is obvious. Everybody wants that. Environmental closed life support system recycling. Even on the space station, this is just in the mid-90s. So there's losses in being able to maintain an environment where humans can thrive. So we need to have power to compensate for some of the challenges of being able to do this on a limited budget like the space station. And the long-term approach for this, that I'll only touch on very briefly, is if we can produce enough fission fuel, then we can power nuclear thermal rockets. And now we can get to Mars in a big hurry, and we can get to main belt asteroids and harvest those for volatiles, such as carbon, the nitrogen that have come up before, and also for platinum. Gold has been studied before. Platinum was studied quite a bit about 10 or 15 years ago. There were a number of high net worth individuals keen on bringing back platinum from asteroids, that seemed to have fizzled out. I think it's because no one had figured out how to do that. So what you'll see here is the foundation for a new approach to be able to get to those very economically beneficial approaches. So it all is based on thorium, and we can find thorium on the moon remotely. So this is from the Clementine mission back in the late 90s. And what you see are those white hot spots are where the thorium concentration could be higher than 12. Later work published in the early 2020s shows numbers as high as 60 parts per million. For this work, everything is assumed to be 20 parts per million, so maybe a little bit hard to find, but not outside the realm of what has been experimentally determined. There is a lot of excavation that's going to be required. So this is the key number on this slide, is this half of a metric ton needs to be excavated in the 1/6 gravity of the moon to get each kilogram of uranium-233. Now that's thorium that we're harvesting, and we're going to transmute that into uranium. Once we have gathered up the regolith in this area that's rich in thorium, an example of that is in crater walls, not at the bottom, not at the crest, but a little bit further down. From the way the moon formed and the way that the soil has been gardened by meteorite impacts, it's expected to be a band around maybe 3/4 of the way up the wall of craters. So in those areas, we'd be harvesting all kinds of different sizes of rock. So we need to be able to reduce the size. The methods used on Earth often rely on gravity to, like a ball mill, for example. The balls inside of the tumbler are returned down, they crush the material through gravity. The moon has not much of that. So we need something that doesn't really rely on gravity, but can certainly use it. So that means jaw crushers and then trommels. A trommel is basically a cylindrical screen that we can use to extract different sizes of material, like a sieve. So a very small jaw crusher is shown on the left. These use a reciprocating action similar to the jaws of an alligator to crush down particles. What you see on the graph on the bottom right was a survey of jaw crushers on Earth for mining operations. None of them are too terribly small in terms of capacity, but in order to do this on the moon, I'll show the timing of this later, we don't need a huge machine. We don't need a very heavy machine. Of course, we want to keep our landed mass as low as absolutely possible. So the extrapolation of this second order curve is around 7.5 metric tons. So that's the value we used with our launch costs. I use conservative numbers for that, so $1,500 per kilogram to LEO, and then 10 times that much for a soft landing in an equatorial spot on the moon. Now we have to take that thorium and separate that from all the rest of the regolith. So the stuff that you're not looking for is called gangue, G-A-N-G-U-E in English. So to get the gangue out of there, we can separate these by density. Thorium minerals are really dense, about 4 times more. Thorium dioxide, for example, has a specific density of 10. Most regolith is in the low 2s, 2.3, 2.5. So we can separate those things with a cyclone, but one using a liquid. And of course, we'd use a liquid, not water, non-volatile liquid like propylene glycol. So what you see here in the bottom left is a senior design team in mechanical engineering, and they built this apparatus to test this out. We used glass beads and iron filings of similar size, and then did testing of this. We used water instead of propylene glycol, and we were able to show a pretty good separation. You have to run through.
They're letting the old gas bags.
Margaret, you might want to mute yourself. All right, so in this way we can get the thorium concentrated. Now we get the thorium. Thorium is called fertile, which means it won't fission in a reactor by itself, but if you give it a neutron, it can become a new compound, and that is fissile. So this is what fertile means. So the thorium is basically one isotope, and then we're going to transmute that into uranium-233. You're probably familiar with the uranium on Earth. Everything comes in 235 and 238. Most of it's 238. And then we have to refine that to get the 235 enriched. That's a really difficult process. And when we take the 235 and fission that, the byproducts stay dangerous for a really long time, much longer than human history. So if we can get this 233 isotope, which doesn't happen hardly at all in nature, when this thing fissions, it has byproducts that decay to safe levels in like 80 years. So we're already on the surface of the moon, so it's pretty easy to, we're already taking care of radiation issues, but by burying this just a couple meters deep, we can make this stuff safe within a century, which is pretty reasonable. So as far as a fission fuel goes, certainly it's not all roses and unicorns, but it's pretty darn good compared to alternatives. So there's two methods of doing this. One is that space is pervaded by gamma rays, and we can use beryllium to produce the neutrons. That's all non-radioactive, but beryllium is super toxic, so we've moved away from that. Instead, we can use deuterium, which is not radioactive. It's about 1 out of every 500 molecules in water. So we bring us a bunch of heavy water and use the deuterium for a fusion process. Now, this used to require really large accelerators, but in the last 10 years, people have developed compact accelerator neutron sources, and these can be used to accelerate deuterium into lithium hydride, but made with deuterium, so lithium deuteride, and those generate a lot of neutrons. So what I've got here is a method by which we can bring non-radioactive materials, so deuterium, and an accelerator, and we can power this first generation with solar power, and then be able to move in a stepwise fashion towards more refined processing to make this uranium. Shown here in the middle of the slide is the nuclear chemistry equation for turning thorium plus a neutron into thorium with an extra neutron. That beta decays within 22 seconds into protactinium. After lunar day, that decays down into uranium-233. In the late 60s, early 70s, the United States pursued a process called the thorex process for using this exact process, technique for turning thorium, which is on Earth 3 times more abundant than uranium, into a alternative to the U-235. This was largely abandoned. It's been picked up by India. So we actually got a lot of our good information from a book from a number of authors in India. But of course, the beryllium is the key problem with this process that we came up originally. And that's what led us to CANS, Compact Accelerated Neutron Source. Shown in the bottom left, this is the fusion reaction sequences of deuterium accelerated into lithium deuteride. So using the nuclear chemistry, this is all detailed in the paper, I figured out what are all the consequent reactions to that. The red neutrons are shown here in these circles. I've got energies from these things, probabilities, so that's all been worked out in a MATLAB program. So we accelerate them. This is a quadrupole magnet into the target. The target spews neutrons out. There's carbon needed to moderate. Carbon doesn't absorb neutrons, but they bounce around in it and they become thermally equilibrated. So they call them thermal or slow neutrons. Once those neutrons are slow, there's a thin layer of thorium. It's hard to see in this image. And that will absorb because the thorium nucleus, once it gets hit by a neutron, it's going to suck it in and start that process. And then there's graphite on the other side. So we're going to lose at least 50% of the neutrons. I'm assuming there's another 50% loss. So everything in here assumes only 25% of the neutrons generated by this target will get into a thorium and transmute that. This is a schematic for the thorex process. I'm not going to go into this in detail, but we have a factory mass here of 10.7 metric tons for this. The TBP is the solvent needed for this process. It can be regenerated on the moon, and we have included that in this mass, but it might be something where we'd want to resupply from Earth, but we're trying very much to reduce those resupplies. Our first design would take 15.7 kilograms of the uranium-235 And usually we talk about things like, well, Peter, is it low enriched or high enriched? This is like, that doesn't apply because it's pure. It's like super highly enriched uranium because we extracted just the U-233 out of the transmuted stuff in our process. So this can fit in a pretty compact reactor. We excavate this thing to make sure habitats can be put reasonably close by. And then we use a Brayton cycle with helium, which turns out to be the best choice for this. And then one important issue is that there's a lot of thermal radiation. With the Brayton cycle, we assumed a 33% conversion to electric power. That means there's 4 megawatts of thermal that has to be radiated into space. At solar noon, that's going to be cut down. So the one challenge with this thing is it's not perfectly baseload power. We have to turn that down by about 20% with moderators at solar noon. But presumably we can make up for that deficiency with solar panels. The NERVA rocket was developed by NASA. They did a lot of studies on this, so we use this as our baseload for doing the designs. This is a lunar factory for being able to make a hydrogen storage. I've got a paper in the AIAA from 2021 on this. And together, that hydrogen storage that we can make all with ISRU materials and with our nuclear reactors running electrolysis plants to extract hydrogen from lunar ice, and the uranium-233 that we've packed in as oxide pellets to make this thing now radioactive. This whole nuclear thermal rocket can be shipped from Earth with no radioactive materials and no reaction mass yet. So we can get that all from the surface of the moon. So with those NTRs, we can go blisteringly fast out past the orbit of Mars. Personally, I don't see any reason to go to Mars. I'd rather go right to those asteroids and start getting those resources. So shown here are some of the numbers for that part of the rocket, and we took the NERVA rocket and scaled that to this mission. So our first mission would be getting these platinum group metals. These are reported to be up to 100 parts per million of metal asteroids. Those are mostly iron and nickel. We assume 20% because that's more well supported, again, making a conservative assumption. These are retorts made of refractory material. This could be thorium dioxide produced on the moon. That's got the highest phase change of any refractory material. I was even called the thorium guy at the US American Ceramics Association because I built the world's largest thorium vessel and then used that to extract oxygen from regolith. We took that up to 2,600 degrees Kelvin and published that. That was on a NASA project. But these things can now be heated by a nuclear source. We can either use fission or fusion. And this phase diagram on the bottom left shows that at this temperature of 1455 degrees C, we can melt this mix of nickel and platinum. Nickel has a higher melting point than iron. Melt off or boil off or evaporate off all the nickel and all the iron and be left with an 80% pure nugget of platinum. So the supports are in here, but they're made transparent in this view. The concept is to put this rail around the asteroid and to have these retorts on a bogie. A bogie is the part of a rail car that sits on the rails, has the wheels on it. So we would use maglev systems, and those maglev systems, electrically driven, would circulate these things at 2.5 meters per second. There'd be a re-railer that puts them on here once they're loaded. And now, as long as they're reasonably circular, we can maintain the material inside through centrifugal force. And once we heat it, then as the iron and nickel evaporate, they're evaporating in a direction off the surface, which will be toward the asteroid. So that's got some interesting aspects to this because the asteroid gets coated in steel. So we could take the steel encased asteroid. It might be difficult to get 100% of it, but we can get most of it while we're in situ out in the main belt with some clever stuff. I'm doing a little bit of hand waving just for this part of it. We could fly this thing to wherever we need it to be. This can be rotated. It's going to have like 2 meters of steel around the outside edge. So this is the seed of a really substantial habitat with radiation protection and artificial gravity. Our second mission could be to get volatiles plus carbon. These aren't going to be of any interest to Earth markets. That's why the first mission was for platinum. I'll show the techno-economic analysis that's really favorable in a minute. Now the second one is going to be, how can we get a lunar habitat to be self-sufficient? So with C-class asteroids, presumably those have all the materials we need for life. So there's ways to process that. I've got a patent pending. I'll show you on the next page. This is a figure from my patent pending on making continuous carbon nanotubes. So we can use those to make tethers, structures, a lot of things you can do with zero chirality carbon nanotubes. So the cost for this whole facility, again, using the 1500 to LEO and then 10x that to equatorial soft landing, is 30.5 metric tons. That's $500 million. Here's the consumables. There should be a dollar sign on that. The excavators are the biggest cost driver, and this could be done in as fast as 5 months, assuming all the engineering gets done in advance. Also, footnote, the cost to do the engineering development, the non-recurring engineering, I neglected that in these costs, assuming it's a lot lower than all these other costs for launches and stuff. So first mission is shown here in this first area, and then this is 6 missions now to the same asteroid. We were going to take an insignificant amount of that per mission. We're only bringing back 45 metric tons of platinum group metals each time, so that's a pretty small fraction. So what this shows is that the two methods can both have a pretty small loss, around $200 million. Okay, that's a lot of money, but I'm assuming that of this whole $2 million per mission cost, everything has to be paid off in the first time, and we don't quite make it, all right? But we know we're not going to do this just once. The world uses about 180 metric tons of platinum every year, so this would not crash the market. But if we had one of these things happen every year, because these are on a 12-month cycle, then you're certainly making money after the second one, and then you're in the range of several billions of dollars of profit by the year 6. So this is not maybe the unicorn that the AI investors are looking for, but from a space standpoint, this is a pretty solid business case. So I've captured a lot of this stuff in books. My textbook, published in 2021 from Cambridge Scholars Publishing, is on ISRU, and this is really designed maybe not so much for those in attendance here who have a lot of experience in this area, but really aimed at the younger people who are trying to, make it out in the space. And then I've got a 3-part science fiction trilogy that covers about a 60-year time span. The main focus at the beginning is space solar power, something I've worked on quite a bit and made a lot of advances on, but then it spins off into some really cool stuff. And I retired as a professor last year, and next month I'll be going back to school as a graduate student in theoretical physics to take some of the ideas that I came up with while I was writing these books and try to turn them into reality. So to summarize, we can use in situ resource utilization for metals, oxygen, thorium, and water. From the thorium, we get uranium. From the water, we can get hydrogen. We can take nuclear thermal rockets out to get some pretty significant profits within a couple of years from harvesting platinum group metals and returning those back to the Earth markets. And then we can start bringing the things needed for substantial size lunar habitats. And then as a long-term benefit, we get the steel enclosed habitat, which we can have a lot of fun with. And also with this, we can go through the whole solar system in human realistic timeframes. So robots, sure, but wouldn't it be fun if people can go there as well? We might be able to have people going out, basing ourselves on Dione, Saturnian moon, and having ships that dip down the atmosphere and maybe get some helium-3 from there. So with that, I'd like to thank you for your attention and welcome your questions.
Fantastic talk.
Thank you.
Yeah, Frank.
Yeah, I was wondering about the applications for fusion, but in a pulse manner, because a lot of people seem to focus about maintaining a continuous reaction, but a lot of simpler concepts could be achieved with pulsing the rockets. Also, thank you for mentioning Titan and the asteroids. I think these will be a crucial component to the whole equation.
Yeah, you bring up an important point on the lithium deuteriide targets. The beam that we need to get realistic yields from this is really high. So if you put that on one target, within a couple of seconds, it's going to melt and ablate away, and it's gone. So I had a separate team of mechanical engineering students do a study of how quickly does that beam heat up the lithium deuteride target, and then we probably need to spread this across many. So rather than having pulsed beams for maximum throughput, we just take the beam and go from target to target to target. So we had like a carousel or an array, and if we can steer that beam in space, then we can spread that heat across those surfaces. They did the full 3D study of the thermal radiation dissipation. In my paper, I do the study of the heat from the neutron absorption in the target and the joule heating. So I've got a cool little figure here with all those at mass and energy balance. And so what they found was with a reasonable size of array, it ended up being like 3 meters on a side. So in space, not too big of a deal, not heavy, but scanning like an old style cathode ray tube. So each target only got hit every, 1 out of 1,000 times. Then we could do the thermal management and get the full yield out of that.
Stuart?
I was looking for I was expecting to hear something about the thorium salt reactor. You must have considered that technology for the reactor on the moon. Can you talk about that a little bit?
Yeah, a great idea for Earth. I so wish that the U.S. would show leadership in thorium salt reactors. They are a good choice on the moon. I've had people suggest to me, they're like, why are you going to so much trouble when you can just bring, your thorium with you and make a salt reactor? And that makes a lot of sense. So I would say that would be a competing idea to what I'm doing. It might end up being a better idea, but I like this one because it's all on the moon. So when you talk to people who don't understand nuclear, they might say the word nuclear, like George W. Bush did. You can say no radioactivity, and they go, okay. And there's one more thing that I should point out. This is another weakness in my argument. When you have a nuclear reactor, before you turn it on, the uranium is no more radioactive than what you find in your countertops if you've got granite or quartz countertops. So until you initiate the reaction, that's when it starts to become dangerous. So nobody would launch a nuclear reactor with already activated fuel. That'd be totally crazy. So if you can convince people that, hey, it's uranium, but it's not like bomb sort of uranium, if people could be educated enough about nuclear chemistry to realize that's probably pretty safe, then you could proceed. But my assumption after dealing with the public for most of my career is that that's not going to fly. So that's why I wanted to have something that was strictly only on the moon, that anything radioactive, because thorium is radioactive, even though it's not fissile, it's still radioactive. All that stuff would be done on the moon.
Good point. Matt?
Hi. I was just wondering if if we put our emails in the chat, could you use that to send us some of the papers that you were discussing?
I can certainly send you the citations. Absolutely.
Yeah, that would be great.
I'll look for that.
Thank you for the talk.
Sure, you're welcome.
Great.